We'd been hiking for 3 days with 3 more to go. The kids were having a good time, and I certainly didn't want anything to spoil the fun. But there was one thing I couldn't ignore. Those high-level clouds with wispy streaks, called mare's tails, are a kind of a cirrus cloud that could indicate an approaching storm system. The prevailing westerly wind has a way of blowing in large weather fronts that can drop a lot of rain or snow. Next day, we got our second big clue, another weather sign. When we looked out that morning, the colored sky reminded me of that old saying, red sky at night, sailors delight, but red sky in the morning, sailors take warning. The clouds were lowering from yesterday's cirrus to what looked to me like altostratus. I knew from experience that rain clouds in the western sky may be colored red by the rising sun. I checked my barometer. The pressure was falling. By now, I knew a storm was on its way and would probably hit us in the next few hours. We decided to stay put for the day or two it usually takes these storms to pass. 2 hours later, a dense layer of nimbostratus clouds was moving in. The pressure kept falling, and then the rain hit us. By afternoon, the wind picked up and it gradually shifted direction. The clouds looked different. The sky had become filled with billowing white masses of cumulonimbus clouds, thunderheads. The next part of the storm was coming right at us. As the big clouds moved over, there were bursts of rain that seemed determined to come through the tents. The rain showers kept on into the evening. Would this rain last all night? It was time to check the barometer again. Finally, the pressure was starting to go up. That meant the storm would be winding down. The next day, we all realized that we had done the right thing in staying put during the storm.
Anyone caught on a lonely seacoast during the passing of a great storm has experienced firsthand one of nature's finest shows. But to understand the storm and its different stages, we need to climb above it and look down on it from above the atmosphere. From space, we can see the storms that cause so much of our weather are not just disorderly masses of clouds. The clouds form a structure, a kind of spiraling swirl that atmospheric scientists call a cyclone. A weather satellite view shows that a cyclone is shaped like a great comma. Putting the storm into motion, we can see how its winds swirl in toward a point. Cyclones travel in zones lying midway between equator and poles, the mid-latitudes. These storms carry enough water to make the mid-latitudes rich with life. Marching across North America, Europe, and Asia, chains of individual cyclones stretch around the globe, moving from west to east with the prevailing westerly airflow produced by the Earth's spin. They should not be confused with smaller rotating storms spawned in the tropics. These are hurricanes, usually much smaller and more destructive than mid-latitude cyclones. But one thing hurricanes and mid-latitude cyclones have in common is that they both develop around low pressure centers, the lows on a weather map. In the northern hemisphere, air spirals counterclockwise around a low. But to understand how these weather systems get started, travel their paths, and eventually die, we have to look at large bodies of air called air masses. An air mass is simply a great volume of air in which temperature and humidity are more or less constant throughout. These qualities depend on where the air mass develops. Over a warm, moist ocean, air becomes warm and moist. If the surface is cold and dry, the air becomes cold and dry. Air masses generally develop in areas of high pressure called anticyclones. From space, these high-pressure regions often appear free of clouds. In an anticyclone, air circulates slowly. These stable atmospheric conditions allow the air plenty of time to take on surface properties and become an air mass. Air masses that move from their source regions into North America are, for example, cool and moist, cool and dry, and warm and moist. The boundaries between air masses are called weather fronts, and it is at these boundaries or fronts where cyclones are spawned. A mid-latitude cyclone plays a role in keeping Earth a livable planet, not only because of the water they carry, but also because of the effect they have on temperature. If there were no way for air masses to interact with each other, warm air masses would continue to get hotter, while cool air masses would get colder. By mixing warm tropical air with cold polar air, the mid-latitude cyclone helps to equalize these temperature differences. But the question that puzzled atmospheric scientists for years was, what actually happens at the boundary between tropical and polar air masses to start a mid-latitude cyclone? A clue was found when military pilots for the first time were able to fly at very high altitudes. Above 30,000 feet, some 10,000 meters, they encountered jet stream winds of exceptional velocity. These high-altitude rivers of air circle the globe at speeds often exceeding 120 miles per hour. You can see how this jetliner's trail is blown sideways as it crosses the jet stream. The northern hemisphere jet stream marks the boundary between warm air to the south and cold air to the north. It was along this boundary that the mid-latitude cyclone began to form in mid-ocean, several days before our students even started their trek. It probably happened like this. Under certain conditions, the jet stream can make air start to rise from the lower atmosphere. As the air rises, it creates a low-pressure area at the surface, and surrounding air begins flowing in. Because of the Earth's spin, air curves and spirals into the low, and a cyclone is born. In the northern hemisphere, cyclones have a counterclockwise spin. In the southern hemisphere, the rotation is clockwise. Either way, cyclones have the same effect. They mix air masses together. Looking straight down, this spiral motion begins to mix the cold and warm air masses. Warm air moves north and cold air moves south. In 24 hours, the mid-latitude cyclone looks like this. Here is what is called the warm front, and here is the cold front. Seen from a satellite several days later, the cyclone has developed a telltale comma-shaped cloud pattern, swirling around a low-pressure region hundreds of kilometers across. Seen as our hikers saw it, the approaching warm front begins with high cirrus clouds. The clouds gradually lower as thicker layers approach, from cirrus to cirrostratus, to heavy altostratus, which thicken to become nimbostratus, rain clouds. From this large expanse of overcast sky, rain or snow begins to fall. A warm front looks like this in cross-section. The warm air, being less dense, rises up over the colder air, forming stratus-type clouds. During this time, the cyclone's approaching low-pressure center was causing the barometer to fall. When the cold front approached, a different array of clouds was seen, the thunderheads of billowy cumulonimbus. This is a cross-section of the cold front. Because cold air is driving under and pushing the warmer air up at a rapid rate, thunderheads form along the front. In a weather satellite picture, the line of thunderheads along the front shows up clearly. Beneath these tall clouds, rain comes in showers and thunder showers, heavy at times. In the late stages of the storm, the cold front catches up with the warm front. The area where the fronts overlap is called an occluded front. Here is the warm front, cold front, and the occluded front. During the overlapping of fronts, the moist air of the warm front has been lifted and trapped above the cold air. This pool of warm, humid air can produce heavy rain. Sometimes, at this stage, the jet stream will separate from the cyclone, stalling the occluded front. Now the energy of a mid-latitude cyclone usually begins to wane, and the clouds break up. Carried along in the prevailing westerly airflow, a cyclone from the Pacific begins to die over the plains. But when it encounters a warm, moist air mass, the storm re-intensifies. Families of cyclones act like giant planetary egg beaters, moving through the mid-latitudes, mixing warm and cold air masses, helping to equalize the huge temperature differences that would otherwise build up between equator and poles. And although they are inconvenient at times, these great weather systems in motion bring the rains that allow life in the mid-latitudes to flourish.
After 2 days of storm, we were finally able to make a fire and dry out. Red sky at night, sailor's delight. It turned out to be true. The next day we had our day in the sun.